You know, you wake up, you make your coffee, check your phone, and you just kind of go about your day.
Yeah, exactly. It's just the daily routine.
Right. And it is so incredibly easy to take your own body completely for granted. I mean, you rarely stop to think about the absolute, just mind-boggling scale of the biological machinery that is currently keeping you alive.
It's hard to wrap your head around, honestly.
It really is. Because right now, you listening to this, you are walking around as a tightly coordinated community of roughly 37 trillion cells.
37 trillion. It's a massive number.
Just staggering. And they aren't just like a massive uniform blob of identical stuff. You have hundreds of wildly different types of cells, right? You've got muscle cells contracting to keep you upright, nerve cells firing rapid electrical signals, skin cells forming this waterproof barrier.
And stomach cells producing literal acid.
Yes,
Yeah.
stomach acid. But here is the puzzle that should completely stop you in your tracks, honestly. You began your life as just one single cell.
Right, one single cell.
That one cell divided into 2, then 4, then 8. And that brings us to the central biological paradox that we are exploring in our deep dives today.
It's a fascinating paradox, really, because every single one of those 37 trillion different cells in your body, they all carry the exact same genetic instructions.
Wait, exactly the same?
Exactly the same. The DNA in that cell producing acid in your stomach is entirely identical to the DNA in the lens of your eye.
Wow.
It is the exact same instruction manual. So the great mystery is, if the manual is identical, how does one single starting cell become a whole body full of such extreme specialists?
Like, how does a cell actually know which parts of the manual to read?
Exactly.
I mean, if everyone is handed the exact same rule book, how do we end up with, plumbers, electricians, and architects?
That is the core question.
And that is the mission for today's deep dive.
Right.
We've got a really fascinating stack of sources to guide us through this today. We are pulling from some recent clinical trial reports, a historical retrospective on a biologist named Shinya Yamanaka, and, well, some pretty alarming investigative pieces on private medical clinics, too.
Yeah, that last part is definitely a wild ride.
It really is. So we're looking into a remarkable entity present at the very beginning of our biological story, which is the stem cell. We're going to examine what they actually are, dig into a Nobel Prize-winning breakthrough that literally rewrote the laws of biology, and, learn how to separate the genuine medical miracles from the really dangerous marketing hype.
And to really grasp that hype and the genuine hope, I should add we have to start with the mechanism itself.
Right, the basics.
Yeah, just as a quick refresher for anyone without a science background on how this works, what makes a stem cell different from a regular cell basically comes down to 2 highly unique traits.
Okay, what's the first one?
First, a stem cell is a renewable source. You see, when the normal cell divides, it usually just replaces itself, and then eventually it stops.
It hits a limit.
Right. But a stem cell can divide and make copies of itself potentially indefinitely.
Oh, wow. Indefinitely.
Yeah. But the second trait is the really crucial one. A stem cell is, well, we call it unspecialized.
Unspecialized, meaning what exactly?
It means it hasn't chosen a career path yet. It possesses this latent capacity to mature into specialized cells later on.
Okay, let's unpack this because I want to make sure we are picturing the mechanism really clearly for you listening.
Okay.
If we think about this in everyday terms, it's like a block of wet clay before it goes into the kiln, right?
Oh, I like that.
Yeah, so while it's wet and it's sitting on the potter's wheel, it has just pure potential. It can be stretched into a coffee mug or flattened into a cereal bowl or sculpted into this tall vase.
I can be anything.
Exactly. But once it goes into that intense heat, right, once it's fired and glazed as a mug, it's a mug forever. It can't suddenly melt down and turn into a vase.
No, it's locked in.
Right. Most of the cells in your body right now are those fired mugs. They are locked in, but the stem cell is the wet clay.
That captures the permanence of specialization perfectly, yeah. And the source material actually uses another really helpful analogy here.
Oh, what's that?
So imagine stem cells as completely blank workers arriving at this massive construction site.
Okay, blank workers.
Right. Because they are completely blank, they can be trained for literally any trade on the site. They can be sent to plumbing school or electrical school or carpentry.
Right, right.
But once they become the electricians and the bricklayers, the specialized cells, they can only do that one specific job.
I see. So a bricklayer cannot suddenly start wiring the building.
Exactly. The stem cell is the raw, untrained material from which the entire specialized workforce is generated.
Which makes total sense when you think about why they are so vital for building a human from scratch. But That brings up a logical follow-up question for
Let's
me.
go for it.
Thinking about my wet clay analogy, is all clay exactly the same? Or are some stem cells more flexible, like more moldable than others?
They are absolutely not all the same. And honestly, this hierarchy of flexibility is arguably the single most important concept in this entire field.
Okay, so what's at the top?
At the very top of that hierarchy, holding the absolute most potential, are embryonic stem cells.
Embryonic.
Yes. These are found in a very early embryo, just days after fertilization, when it's really nothing more than a microscopic ball of maybe a few dozen cells.
And what gives them top-tier status? Like, why are they the ultimate wet clay?
Because at that specific, really early stage, those cells are what biologists call pluripotent.
Pluripotent. Okay, that sounds like a word we need to define.
It is a foundational technical term for us today, definitely. So, pluri meaning many, and potent meaning powerful or capable.
Many powers.
Right. Pluripotent means they have the ability to become virtually any of the hundreds of cell types in the entire human body.
Any of them at all?
Any of them. There is no biological door closed to them yet. From a medical standpoint, that ultimate flexibility holds just massive promise.
Because you could fix anything.
Exactly. Theoretically, you could use pluripotent cells to replace any damaged tissue anywhere in a patient's body.
Now, it's really important to look at the history here, because obtaining those incredibly flexible early cells meant using early human embryos. And that placed scientists right in the middle of a profound and honestly an entirely valid ethical debate.
It certainly did.
And I want to be super clear with you, the listener, right now. Our deep dive today takes absolutely no sides on this debate. We are just impartially reporting the history here. Because thoughtful, reasonable people held very deeply varying views on this, the field was historically quite constrained.
Very constrained.
Regulations were intensely debated, and funding for research was heavily restricted as a result.
And that historical context is crucial because it really explains the intense pressure that the scientific community was under at the time. While that debate over pluripotent embryonic cells was raging, researchers were simultaneously relying heavily on a different, much less controversial kind of stem cell.
Pressure what?
Adult stem cells, or they're sometimes called tissue stem cells. And you actually have these inside you right now.
Wait, really? I have stem cells in me right now.
You do, yeah. Your body keeps this hidden reserve of them tucked away in various organs throughout your entire life.
So are the ones floating around inside me the wet clay kind? Like the pluripotent ones that can become anything?
No, and that limitation is the key difference here.
Okay.
If embryonic stem cells are the ultimate blank workers, adult stem cells are more like specialists' apprentices.
Specialist apprentices. Got it.
Right. Their entire job is localized repair and replacement. They exist just to restock the cells that you lose to everyday wear and tear.
So it's just patching things up.
Exactly. So your skin, the lining of your gut, your blood, these tissues are constantly being turned over and renewed by resident, local, adult stem cells. But they have strict biological boundaries.
Meaning they can only replace what's in their immediate neighborhood.
Precisely. So an adult stem cell living in your bone marrow can divide and produce all the various types of blood cells you need, red blood cells, white blood cells, platelets.
Right.
But it cannot suddenly decide to become a brain cell or a heart muscle cell.
Because it's locked into the blood department.
Right. The chapters in the instruction manual for making a brain cell have been permanently glued shut for that bone marrow stem cell.
But, okay, I'm stuck on something here. Even with those limits, we've used adult stem cells with massive success.
Right, yes.
Because bone marrow transplants are literally a stem cell therapy. And we've been using them to treat leukemia and blood diseases for decades.
That's entirely true.
When a patient gets a transplant, they're just getting healthy, blood-forming adult stem cells. So if adult stem cells, which, we get from consenting donors with zero controversy, are already saving lives, why was the field so obsessed with the controversial embryonic ones?
It all comes back to that word, pluripotency.
The ultimate flexibility.
Exactly. Adult stem cells are fantastic if the problem is in the blood or the skin. But what if a patient has a severed spinal cord and needs new nerve cells?
Oh, right.
Or what if they have had a massive heart attack and a large section of their heart muscle is just dead?
A bone marrow stem cell simply cannot fix a spinal cord.
No, it can't. A skin stem cell cannot patch a heart. Their biological doors are firmly locked. So to repair the most devastating complex injuries and diseases, scientists desperately needed the limitless flexibility of those embryonic cells.
So the field was facing this seemingly impossible gridlock. We desperately needed the limitless flexibility of the embryo to cure major diseases, but we were constrained by the ethical realities of obtaining them.
It was a huge bottleneck.
But then somebody figured out how to cheat the system entirely.
Well, I wouldn't call it cheating. I'd say they completely rewrote the rule book of biology.
Okay, let's talk about Shinya Yamanaka in 2006.
Yes. In 2006, Yamanaka, who is a Japanese researcher, asked what was, at the time, a completely audacious question.
Because people thought it was impossible, right?
Totally impossible. For decades, the prevailing assumption in biology was that cellular specialization was a strict one-way street.
Once a fired mug, always a fired mug.
Always. But Yamanaka wondered if that was truly an unbreakable law.
Okay.
He asked, could you take an ordinary, fully specialized adult cell, let's say, just a plain, boring skin cell from your arm, and somehow force it to wind its biological clock backwards?
Wow.
Could you pry open those glued shut chapters of the DNA manual and revert that skin cell back into the flexible, pluripotent state of an early embryo?
Here's where it gets really interesting, because he didn't just pose the question, he actually figured out how to do it.
He did.
And reading this, it really reminds me of hitting a factory reset button on a smartphone.
That's a great way to think about it.
Yeah, imagine your skin cell as a phone you've owned for years. It's filled with very specific apps for protecting your arm. It has a customized layout. It's just bogged down with years of specific data.
Lots of baggage.
Exactly. What Yamanaka figured out how to do was access the hidden developer settings and hit factory reset. You wipe the cell completely back to its original out-of-the-box state, where it is a blank slate, totally clean, and ready to be programmed into whatever you want.
That is exactly what happens at a genetic level. And what's fascinating here is how he managed it.
How did he?
Well, out of the roughly 20,000 genes in the human genome, Yamanaka relentlessly tested combinations until he found just 4 specific genes. They're often called transcription factors.
Just 4 out of 20,000.
Just 4. And when he introduced just those 4 factors into an adult skin cell, they acted like master keys.
Incredible.
They unlocked the closed sections of DNA and initiated a chain reaction that completely stripped away the cell's specialization.
We have a specific name for these reset cells, right?
We do. We call them induced pluripotent stem cells, or IPS cells.
iPSL.
Right. Induced because we force them to rewind into this state, pluripotent because they regain the power to become anything, and stem cells because they can, once again, divide endlessly.
But wait, I have a timeline question for you. The sources note he published this in 2006, and then he won the Nobel Prize in Medicine in 2012.
Yes.
6 years from discovery to a Nobel Prize is basically overnight in the science world.
It is unheard of.
Usually it takes decades. Why did the Nobel Committee rush to crown this specific discovery so fast?
Because in one elegant mechanism, he solved the 2 most massive bottlenecks in regenerative medicine at the same time.
Which were?
First, he completely sidestepped the ethical dilemma we talked about. You no longer needed human embryos to get pluripotent stem cells. You just needed a simple skin biopsy from a willing adult.
Right, of course.
But second, and medically, this is arguably just as profound, he solved the immune rejection problem.
Oh, right. Because immune rejection is the absolute bane of organ transplants.
It ruins everything.
Yeah, if you use an embryonic stem cell from a donor to grow replacement heart tissue for me, my immune system is going to look at that tissue, see foreign DNA, and attack it like a virus.
Exactly. Your body is designed to destroy absolutely anything that isn't you. But with iPS cells, a doctor can take a sample of your skin, hit the factory reset button, turn those cells into your heart muscle cells, and implant them back into your chest.
And your immune system just accepts it?
It recognizes the DNA. It sees them as self. There is no rejection at all. It is perfectly matched biological repair material, literally custom made for the patient.
Okay, so science now has this miraculous factory reset button. We can take a skin cell and turn it into a heart cell or a nerve cell. But let's look at what is actually happening out in the real world with this right now.
Good idea.
Because regenerative medicine, printing new body parts, it sounds a lot like science fiction.
It does, which is exactly why we have to clearly separate the methodical, proven science from the predatory marketing.
Yes, let's do that.
So the genuine promise of iPS cells generally falls into a few distinct buckets. Regenerative medicine is definitely the most famous one. This is the dream of growing replacement cells to repair damage, like growing new insulin-producing cells for people with type 1 diabetes, or replacing dead heart muscle after a heart attack.
But are they actually doing that yet, or is it all just, lab theory?
It is actively moving from theory to reality right now. There are actual clinical trials underway, and a handful of specialized treatments have reached official medical approval.
Really? Like what?
For example, using stem cells to repair severe chemical burns or damage to the cornea, which is the surface of the human eye that is a reality today.
Wow.
But we're also seeing massive leaps in areas you might not expect.
Yeah, I was reading in the clinical reports about something called disease modeling.
Huh? Yes.
It mentioned growing a patient's diseased brain in a dish.
Yeah.
How does that actually work? Because frankly, that sounds incredibly dark.
It sounds super dark, yeah, but it is an absolute game changer for research. Imagine a patient has a severe, rare genetic brain disorder, like early onset Alzheimer's.
Okay.
It is incredibly dangerous and invasive to take biopsies from their living brain to see what is going wrong at a cellular level, right?
Obviously.
But with IPS technology, scientists can take a harmless skin cell from that patient's arm, factory reset it, and then program it to develop into a neuron in a laboratory dish.
Wait, so you are literally growing that specific patient's exact genetically identical brain cells in a petri dish?
Yes. And because it has the patient's DNA, that lab-grown neuron will develop the exact same Alzheimer's pathology as the cells inside their head.
That is wild.
Researchers can study the disease up close in real living human tissue without harming the patient at all.
And I guess they can test drugs on it.
Crucially, yes, they can test experimental drugs on those lab-grown cells to see if a medicine stops the disease safely, long before they ever risk giving that drug to a human being.
Okay, so that is the slow, careful, methodical march of real science.
Yes.
But we have to pivot to the dark side of this industry now, because the gap between that slow scientific promise and fast delivery is currently being filled by what can only be described as a wild west of hype.
It is absolutely a wild west out there.
Around the world, and heavily across the internet, private, totally unregulated clinics are advertising stem cell treatments for basically everything under the sun. They promise to cure arthritis, reverse autism, fix multiple sclerosis, and essentially cure aging.
And they do it at exorbitant expense, usually entirely out of pocket, and almost always without any solid, peer-reviewed evidence that the treatments actually work, or more importantly, that they are even safe.
Right. So what does this all mean for you, the listener, if you're scrolling your social media feed tomorrow and a glossy, targeted ad pops up promising a $10,000 miracle stem cell injection to fix your bad knee by next week? Like, what is actually in that syringe, and what is the real biological risk?
Right.
Because I think a lot of people assume, well, at worst, it just doesn't work, right?
That is a very common, very dangerous misconception. At worst, it can be fatal.
Fatal.
Remember what we said about pluripotent stem cells? They have the power to become anything.
Right.
Turning a cell with pure potential into a safe, reliable treatment is extraordinarily difficult. You have to guide it into exactly the right cell type, you have to get it to the exact right location, and crucially, you have to ensure it knows when to stop growing.
Because if you just inject unspecialized cells into a knee joint.
Well, think about the blank workers. If you drop a bunch of blank workers into a construction site with no blueprints, they don't just quietly build a wall.
They just do whatever.
They build a chaotic mess. A pluripotent stem cell placed in the wrong environment without precise chemical instructions to become cartilage won't magically cure your knee. It will just start dividing chaotically into whatever it wants.
Oh my God.
It can form something called a teratoma, which is a tumor made of a random mix of tissues like teeth, hair, and bone, growing right there in the joint where you injected it.
Wow. Okay, so the contrast there is incredibly stark. On one hand, you have this slow, careful, methodical science working in heavily regulated trials to ensure you don't grow a bone tumor in your knee.
Right.
And on the other hand, you have fast predatory marketing promising you the fountain of youth right now, as long as your credit card clears.
Precisely. The honest scientific position right now is that stem cells are a spectacular area of research with immense potential. But currently, we have a very small specific number of proven therapies and a massive number of possibilities that are still being very carefully worked out in clinical trials.
So to bring this all together for you today, the most reasonable way to hold all this information is with a balance of immense hope and steadfast patience.
Well said.
Stem cells genuinely are the body's master builders. The fact that modern biology uncovered the mechanism to literally rewind the clock on a specialized adult cell, bypassing ethical gridlocks to create a custom-matched master cell, is just a staggering triumph.
It truly is.
And real, life-altering treatments are making their way through clinical trials right now. But when you see a headline or an ad promising a miracle cure by next month, the appropriate response is deep skepticism.
Absolutely.
The science is thrilling precisely because it is complex. And the best way to honor that science is to insist on evidence, not to let desperation outrun the data.
And if we connect this to the bigger picture, especially what we discussed regarding rewinding cells and all that hype around aging, this science leaves us with a truly profound philosophical question to ponder.
Ooh, what's that?
Well, if science has proven beyond a doubt that we can successfully wind back the biological clock on a single specialized cell to a perfectly young, unspecialized state, what does that mean for the biological limits of the human lifespan?
Oh, wow.
Right. If our cells can literally be hit with a factory reset, are we just a collection of clocks waiting for the right combination of genes to rewind us?
That completely reframes how you look at getting older. You started as one single cell. And now, hidden inside every single one of those 37 trillion cells you are walking around with is the dormant instruction manual to potentially wind back the clock.
It is the ultimate paradox of biology, just waiting to be solved.
Definitely something to think about the next time you pour your morning coffee.